Want to start out, yeah, okay, that's a pretty comprehensive introduction. So the burning question should be, why create an advanced scientific instrument disguised as a toy? That's our basic premise, is expanding science by just making it as fun and easy as possible to actually do fairly complex things. So I like to, ideally, my the first time you see the Nanopore 64, like Nuno mentioned, I have a theatrical background, and I just have a strong sense of wanting people to connect emotionally to science now that I'm a scientist, and that's not what I'm nominally supposed to be doing. Not making art, but making science, but it all comes together. So I want to show a video we made, just about 1 minute and 20 seconds, that shows the thing that we're building, and that will hopefully make you hungry to know more. So I'm going to pull that up and let it speak for itself. Make sure at home that your volume is turned up as loud as possible, and that you're in a dark room if you can. Treat this like a theatrical experience. Okay, here we go. All right. I hope that was lots of fun for everybody who witnessed it, and that you could hear "Also sprach Zarathustra" announcing, I guess in 2001 it was meant to be, this is a leap in man. Wait, anyway, you all get the semiotics of that. So yes, let's take the bio by the horns. The Nanopore 64. It's a scientific instrument, but it's also a gaming console. So what I'd like to do now is take a quick, complete right turn. And I want to talk about Nanopore Science, and it's going to be quick since we started a bit late. I'm going to go through some Nanopore Science, just kind of on background, and then I'm going to come back. I'm going to talk about the visionary stuff. I'm going to talk about the console itself, but I want you to hear about the science, and this is going to be rapid fire because I want to get back to the game. Okay, so we're going to look at Nanopore basic science background because I want you guys to have it, or kind of frame things in a certain way. So new directions in science are launched by new tools much more often than by new concepts. The effect of a concept-driven revolution is to explain old things in new ways. The effect of a tool-driven revolution is to discover new things that have to be explained. And I think there's a ton of new things that have to be explained, and that's why we're obsessed with new tools. This is a list that Eric Topol made just a couple of years ago of all the really basic things that we kind of thought we knew about human biology that were upset by new data that we kind of thought were canonical. Yeah, really a heck of a lot left to learn. So I went down the path a while ago of thinking, what's the most powerful general purpose molecular and cellular sensing technology? The tools that we use as scientists, and the tools that we use as scientists, they can be a ton of different things on a big floor, tens of millions of dollars of high-end equipment that's complex and expensive to use, and things that many of us listening and many of the presenters will have also used: optical microscopy, electron microscopy, scanning tunneling microscopy. Mass spec should be in there, as well as 50 other things, and all these other different ways of looking at and seeing biomolecular reality. And we began the company, which was originally called Nanopore. Then we had to change the name because of the current environment. Had nothing to do with demons, just Maxwell's demon. Look it up. And Nanopore Sensing took Nanopore Sensing and made it super dynamic across this wide range. This basic tech goes back to the 1950s, even earlier. The first nanopore was just a hole poked in a cellophane wrapper on a pack of cigarettes. And Nanopore Sensing has this ridiculously wide range of applications. I'm just going to scoop past it. You can also I'm going to list some examples in case you're not a Nanopore sensing or resistive pulse sensing geek. Just stuff that things passing through a little hole making a signal can tell you. So you get distinct physical signatures for circulating tumor cells, for instance, with the right size pore. Basic idea came about in 1989. David Deemer's notebook, pass things through a tiny pore, and they create current changes. And he has this framed on his wall at UC Santa Cruz. And also, late work in the 90s, a lot of struggle. More than a decade, billions of dollars to be able to in this case, this was just the first time they could tell some kind of difference of hardened sequence. So this is I think late 90s. A long run of C's versus a long actually this is just RNA versus DNA. This kind of shows that if you make a scatter plot of the different durations and shapes of the spikes, this is going back 25-ish years, 20 years, you get these different buckets into which things can be parameterized. And that's how you can tell things apart based on the sensing modality. Fast forward, $1 billion of investment, a few hundred research groups, you've got all these different ways to make tiny holes in thin materials. And part of our mission overall is to figure out which of these are going to act as utility scale molecular sensors. We'll get back to that when we get back to the visionary stuff. This is another thing, just an example of kind of cool, crazy things people have played with. Once you get the basic idea down, you see things like, well, you can take a little glass rod, pull it out, snap it in the middle with literally probably a laser in this case with mechanical tension. And the thing has a membrane running down the center, and out at the end of it, you get at the end of that, like the snout on a pig here at the end, is a double nanopore. And the signal comes from molecules coming over that wall in what they call a zeptoliter bridge, just this tiny amount of solution hanging out right there at the bridge. I'm bringing this up because if you're a creative and imaginative researcher, you just spent time thinking about this particular technology, sensing how things flux because something else passes through a tiny hole, is 100 different crazy things like this work and propose interesting directions in controlling things at that scale. And also, you're not just limited to blocking ionic flux, but you can also complete circuits like this work that was done with gold electrodes and a piezo. And there's also optical detection, which scales in different ways. And there's another thing. If you've never heard of nanopore sensing, you think from first principles, you immediately go, well, why can't we ping pong back and forth to integrate a signal? And yeah, that's another part of the toolkit, another thing you can play with. And in fact, the power of that sort of modality eventually, in some researchers have shown a few, at least one published paper looked at integrating a ton of these signals and from individual translocation events. And the crazy thing about that paper was that they were able to show literally like cubic sub-angstrom precision in measuring super tiny differences in these nanoparticles. Again, if you have that kind of resolving power, it suggests all kinds of really cool things are further down the road. One of our SAB members is one of the authors on this paper, so we're very familiar with it. Where those spikes that you see in current data, they can be parametrized in a lot of interesting ways. And in this paper, they were able to do they were able to parameterize single protein events into 5 dimensions to be able to sought to identify all these different proteins label free. And that work has even been extended on and shown a lot more promise and continues forward. Also, I'm working with the very good friend who is the first person ever label. Well, I haven't worked with her directly in several years, but I've been cheerleading her on, and we did some early conceptualization several years ago about this really cool idea that surprisingly worked to make specific sort of Morse code road bumps on the backbone of DNA. And I'm very proud of the work because it was actually very early. And this is the main commercialized instrument in nanopore sequencing, which is the workhorse, the most important thing that nanopores can do, and the sort of raw data that you get. I like to show this to people because it's important to note that we're not at the point where you can look at these signals and you can go ATCG by eye, because it's still too complex and fuzzy with all the Brownian motion and uncertainty down there at the pore and the signal that you're getting. So you got to throw a lot of machine learning at it, which is interesting. Yay, we said the machine learning word. Okay, so rushing forward, we're going to go into the vision stuff. I wanted to give you a little bit of meat first. So Molecular Reality Corporation, formerly Demonpore, still technically Demonpore, but DBA, Molecular Reality Corporation. And our flagship product is the Nanopore 64. Hope I can get it to all of you conference participants, and all of you will be playing with it. I've got a prototype sitting here 6 inches from my hand, and we are hard at work so we can start shipping these out. Yay, Nanopore 64, isn't she pretty? And that thing you see there, electronics are real, etc. The nanopores are real. We are struggling to, well, I wouldn't say struggling. Well, okay, struggling is honest. Engineering is hard. But we are very close to basically being able to ship these nanopore cartridges with this thing and let people play molecular games. And you will hear more very soon. And there's some stuff that we're only going to be telling investors in the next couple of weeks. That being said, we are still open to accredited investors talking to us. And if you want to see the cool stuff behind the scenes, you should get on board before that happens, for a live presentation that will happen soon. So our vision is named for the company is the vision, molecular reality. Give everyone the power to see and understand molecular reality. And it's going to be indispensable that a huge number of people can see, easily look at what's going on in the world around them in terms of cells and molecules. And it's indispensable to solving the world's problems, and it's going to expand culture, consciousness, and creativity in ways we can barely imagine. And we have these big, hard problems that we're all here to talk about. Hundreds of thousands of people dying every day of age-related diseases, just killed millions of people at a big pandemic. Worst pandemics probably on the way eventually, inevitably. Climate change, burning, drowning, blowing down the world, epidemics of despair, material and energy scarcity, having all our eggs in one planetary basket. And these problems demand civilization scale resources and determination. So what can one little startup move? How can we move the world? Well, we need a lever and a place to stand. Biomedicine and synthetic biology, that is our place to stand. That is our field. I think those are the things that I can see as things that will fundamentally change everything for us in an overwhelmingly good way. And I don't want it to take several decades for those dreams to come to fruition. So our goal is utility scale molecular sensing. Okay, I'm gonna tell you what we need for that. So a candidate technology that would just be all around us and everywhere, and anyone can use it. You take it for granted. It shouldn't need labels. It should be long-lasting, easy to use, cheap. You should forget that it's there. It should be able to get some kind of signal from anything so that it's not reagent limited, and it should be compact. So all of these things, the path is, I think, solid-state nanopore sensing. So solid-state nanopores are going to provide the backbone of utility-scale molecular sensing, in my vision. In our vision, they're compact, they're label-free, long-lasting. So many of these things have already been shown. There's ridiculously high potential for throughput, and certain types of nanopores that we've worked on have the potential to act as universal single-cell molecule sensors in a single compact platform. But we're not there yet. That technology is not there quite yet. The theoretical potential is not yet realized, still to be proven and made robust. A whole bunch of us think in the community we can sequence DNA with solid-state nanopores, and some people have gotten close, and I've worked with some of the people who've gotten closest. That can be done. We also need label-free multiplexing. We eventually want to be able to detect individual analytes across 8 orders of magnitude in volume with the same instrument. And there's room for orders of magnitude improvement in throughput as a function of cost. So the field exists and has billions of dollars a year in funding because we think we can get there, but it won't just happen. Okay. So nuclear fusion gets 1.5 billion a year. Actually, solid-state nanopore R&D is probably 100 million a year. That's actually the right estimate, distributed across the world in a few hundred groups and several startups. But unlike nuclear fusion, you can't give everybody a tokamak reactor to play with, but you might be able to give a ton of people a Nanopore 64 and the instruments that will come after it that will actually do FDA-approved diagnostics. So molecular gaming is our first killer app for nanopore sensing. And we want professional scientists to be able to coordinate experiments at an unprecedented scale by people dumping things into nanopores from around them and inside them and things that we send them, and doing it in interesting, thoughtful ways. So fundamentally, if we can make player science the thing that we do to democratize science, you would just inherently solve the reproducibility crisis. Because if something doesn't work, people would just be immediately unable to repeat it if we're all doing the same things. This is also the path to the molecular PC in my mind, but it's a much bigger, it's a bigger opening into that river than the molecular PC because it's like weird and fun, yet it relates to this really hardcore science. But you don't need to think that you're as smart necessarily as the early Uber geeks of the early 70s computer science revolution to want to just take part in it, to just shoot aliens that are generated by molecular signals in nanopores. And that's what we're going to be showing some people soon. And if you get on board, you'll be the first to see it. These are some of the games, some of the areas of the games. that we're designing. If you go to our website, molecularreality.com, you'll see fuller descriptions of the games themselves. And we do think this is something people want. I think my favorite comment on it is someone who maybe did not have English as a first language said, "This is no C before." And I just love that. That's my favorite thing anybody has said about what we're working on. This is more about our traction, where we're at quite precisely. This is kind of the idea that we're not trying to get a big chunk of the global video game market. We're trying to get a big chunk of the global biotech services market in a very indirect way. And the future, we hope, is that starting latter half of this decade, we are installing we're installing the backbone of utility scale molecular sensing everywhere in the world. That is the dream. All right, thank you for your attention, and I hope we had no IT glitches during all of that.